Okay, guys, so this is the chapter 3 video. Hopefully you're watching this. I'm sure you are if you're listening to this. Talking about different functional groups that you can expect to see this semester and next semester. Some of these we're going to cover this semester, mostly carbonyl and aromatic will be covered next semester. And so organic functional groups give an organic molecule their chemical and physical properties, melting points, boiling points, whether or not we're going to add to them or whether or not we're going to substitute them like in a double displacement reaction. Okay. And so don't stress out a lot about any type of chemical reactions that you might find in chapter 3. Pretty much the second half of organic 1, we're going to start talking about those chemical reactions in gory detail. So just focus on being able to identify them and areas of polarity if there are areas of polarity. Okay. All right. So we have a bunch of different functional groups in organic chemistry. Okay. But we're only going to talk about a few here, but we're going to focus on the most basic of all the functional groups. And all they are is just a specific group of atoms within a molecule that have characteristic properties and reactivities. All right. Different types of functionalities that you're going to see this semester, okay, allow us to predict what type of reactivity that we're going to have. So we're going to have a pi bond here. And so this is chapter 9. I'm sorry, chapter 10 is where we're going to talk about the reactivities of these types of functional groups. Molecular classification. In other words, we have specific names for all of these functional groups. Most of you guys have heard of alcohol, but alcohols are an entire subcategory of compounds that have an OH group on them, okay? And as a result of that, they also have very specific nomenclature. Now, we're not going to even talk about nomenclature until chapter 4, and there won't be any nomenclature on the first exam, okay? But I want to talk about this little R guy right here, okay? Some of you guys may have paused the video and looked on the periodic table for the elemental symbol of R, and there isn't one, okay? And so we use R in organic chemistry to serve as just a placeholder for a generic carbon chunky. For example, I could have this, where this would signify the R group. I could have something like this, something like this, where in this particular case, all of this carbon stuff over here would signify the carbon chunky. But what's important here is that both of these guys have an OH group. So both of them have the same type of functional group attached to them. Again, don't try to figure all this out at once. We're going to do this. This is chapter 9 for OHs, and we're going to do this a lot, okay, going forward. Okay, just right now, again, just try to get familiar with this stuff. Synthesis of mechanism. So how to make these compounds. So how to make them and what type of chemical reactions they can undergo. So, you know, when we were talking about double displacement or single displacement reactions in Gen Chem, okay, we could predict what salts we needed to use to make insoluble salts. You could predict which elements you needed to make, for example, water. You know that you would have to pick hydrogen and oxygen, okay? And so it's like that. Of course, you know, it's going to be a little bit more complicated. But for this particular class, a lot of times you're going to have carbon attached to some other non-metal that's not hydrogen, and that will allow us to predict chemical reactivity. And so for this semester, the chemical reactivity is going to be right here. So the carbon attached to an oxygen atom or a nitrogen atom or a sulfur atom or halogen, so chlorine, fluorine, bromine, or iodine, and whatnot. Okay. Not so much this semester, but next semester for sure, we're going to talk about biological activity. And so again, this is what we call an amino group. And so many of you have heard of compounds called amino acids, and guess what? They have an NH group as a part of them, hence amino acids, and they have biological activity. Okay, some of you might know that that amino acids tend to make up all of our proteins. All right. As a result, non-amino acids, amino compounds, can be very toxic, which means they're basic, but they also can be very dangerous because your body can sometimes mistake these for amino acids. So again, toxicology, carcinogenic, okay, teratogenic type behaviors, stuff like that. Okay. And good old physical properties. Now, I prepared another video to discuss the physical properties, but just real quick, we have salts in organic chemistry. And so we know that, for example, sodium chloride is a salt, just like this guy right here has a metal and a bunch of nonmetals. So this is also a salt, okay? In other words, it's ionic. And just like most salts, this is called an alkoxide. It's mostly soluble in water and have high melting points. So I know a lot of you guys might have heard that general chemistry doesn't have anything to do with organic chemistry, but no, it's absolutely incorrect. Every chemistry after general chemistry is applied general chemistry. So we taught you all that stuff in Gen Chem, and in all the other chemistry classes you guys are going to take forward, we're going to apply them to very specific types of compounds. Okay? So, real quick, I'm going to identify some very small way of identifying specific types of atoms. Okay? We use the word heteroatom. Okay? Heteroatom is just a generic terminology. We use the symbol Z, and Z could be oxygen, nitrogen, sulfur, phosphorus, fluorine, bromine, or iodine. It's basically any other carbon or non-hydrogen atom. So this is not a C or an H. Okay. And as we told you in chapter 1, all of these bad boys are what? Well, they're electronegative, right? And as I told you again in chapter 1, carbon has a very specific type of functionality, physical property, and that it's electropositive, right? And so the nice thing is, if you remember from Gen Chem 1, which I know every single one of you guys did, and we were looking at polar covalent bonds, we were looking at polar covalent bonds, we had to have a different electronegativity between 0.4 and 1.8, okay? And yet if I look at carbon and iodide, carbon has electronegativity value of 2.5, iodine is 2.6, but because iodine is electronegative, and carbon is electropositive, right? We don't really focus on that difference anymore. Okay, we look at what's bonded to carbon. As long as it's a heteroatom, okay, you're going to get a momentary dipole and an actual dipole going straight through the middle, going straight through the middle of this bond right here. All right, so we're going to have a partial positive here, partial negative, okay? And so, again, these are things that you just kind of got to realize, and it kind of makes your life a lot easier. Pretty much any heteroatom to bonded to carbon, you're going to have a partial positive spot where the carbon is. And for everything that we're doing this semester, okay, with the exception of alkenes, which I'm going to talk about in just a second, that's where the chemistry is happening, folks. That is where the chemistry is happening. And here are some examples of a carbon heteroatom molecules. We have an OH, okay? Dipoles going this way. We have an NH2, dipoles going this way. We have an RX. And so again, remember, X is equal to what? Fluorine, chlorine, bromine, and iodine. Now, this is more of an organic 2 thing right here. This is what we call a carbonyl. But again, we have a dipole going from the carbon to the oxygen atom. Okay? And so, in addition to knowing where the dipoles exist, you're also expected to know the geometry around each atom in a molecule. For example, if I were to have something like this, okay? So if I were to have something like this, Yeah, let's stop there. Okay. Oopsie, let's erase one of these things right there. There we go. And so we've already taught you about skeletal structure, so you know that all the lone pairs are implied. Okay. You know that there's a carbon here. Okay, carbons are implied, hydrogens are implied. And so when we're talking about geometry, we're only talking about central atoms, right? So fluorine is not a central atom, so we don't care about its geometry because it's a terminal atom. But you would need to know that this is tetrahedral. This is bent. Okay. All of these carbons right here are tetrahedral. This amino group here is what we call trigonal pyramidal. Okay. This phosphorus right here is also bent. Okay. This carbon right here, because it's sp2, is trigonal planar. Okay. And of course, this terminal carbon here is also tetrahedral. Okay. And so again, just you need to know the general geometry because starting in chapter 7, geometries are actually going to be used to predict the outcomes of these chemical reactions. And that theme is going to continue on until you finish with organic chemistry. All right. So hybridization. Okay. Again, let's go back and let's list the hybridization of all of these. Fluorine is sp3. This carbon is sp3. This oxygen is sp3. This carbon is sp3. This is sp3. This is sp3. When I get over here, I've got a couple of sp2 atoms next to each other. And then this terminal carbon is also sp3. And so we're going to, hopefully by the time you watch this video, or unless you're getting an early start, hopefully by the time we watch this video, I will have covered this material this week in class. Today's Memorial Day, in case you're wondering, class starts tomorrow for me. Okay, you will have covered this information in class, and you'll be a lot more comfortable with this than if you would have. If you haven't come to class yet, or you haven't watched the videos, or for whatever reason, this will become a lot easier the more you're exposed to it. Okay. All right, so let's talk about some of these types of functional groups. Okay. The most basic of all organic molecules are what we call hydrocarbons. And as the name implied, it simply has some number of carbons followed by some number of hydrogens. But what's important is those are the only two atoms that are in the molecule. We don't have any heteroatoms. We don't have any ions. It's just plain Jane carbons and hydrogens. Okay. These are not as sexy as the other ones, but they're incredibly important. Alkanes. Okay. This is what we use to power our world. And here, all of my carbons are sp3. Alkenes, which, oopsie, I had a typo here. My bad. Let's change this right here. And let's change this right here. And let's put a double bond here. Let's put a 2 here. And let's put a 2 here. So in alkene, we have at least 2 sp2 hydrogens that have a carbon-carbon double bond. At least one. Okay, next semester you're going to find that we have what are called dienes and trienes. They have multiple carbon-carbon double bonds, but to be an alkene, you need just one. Okay, the last one is what we call an alkyne. Okay, and so these are triple bonds. Okay, and so for here is, again, depending on when you're watching this, you have 1 sigma bond and then you have 2 pi bonds. Okay, but it's a triple bond that makes something an alkyne. And this is actually kind of interesting if you look at how this is set up. Okay, you have alkanes, anes, A, alkenes, E. Okay, and alkynes starts with a Y. So if you look at this, A, E, Y, right? It's arranged in alphabetical order. And then you have all single bonds, at least one double bond, and at least one triple bond here. And again, this is just talking about hydrocarbons. If we start adding in carbon and heteroatom bonds, then they're no longer hydrocarbons, and we no longer use the term alkanes, alkenes, and alkynes. Okay? And so they come in a bunch of different flavors. Okay? Aliphatic is just Again, just a different way of saying it is a hydrocarbon group or an actual hydrocarbon molecule. So for example, if I have something like this, I could say this R is aliphatic. And so that means that this Z right here is the only heteroatom existing in the molecule. Okay. They are what we call acyclic aliphatic compounds, right? And so acyclic means everything's a chain. It can either have these things coming off that we call branches. It can be double, single, triple. Okay, but at the end of the day, it's just carbons and hydrogens in a straight line. Okay. The opposite of acyclic, of course, is cyclic. Okay. Probably something you never thought about, that hydrocarbons or molecules themselves could be cyclic, but a lot of molecules are actually. Okay. And so, but again, we're only talking about hydrocarbons. So this is a ring of carbons that are 5. So we call this a pentene. Ene, because it's an alkene, because it's got that double bond. This next one we call, actually it's called cyclopentene, my bad. The next one would be cyclobutane, because why? Because all the carbon-carbon bonds are single, right? All the carbons are sp3, okay? Again, don't stress out a lot about knowing these names, because you're not going to have any nomenclature on the exam, and every nomenclature will be covered when we cover that specific functional group in gory, horrific detail, okay? The next type of cyclic compounds I'm going to talk about, not necessarily just hydrocarbons, or something called aromatic. You will also hear these you'll hear them referred to as aryl. Okay. Aromatic compounds are very special. They have alternating pi bonds, and they can resonate, and they have incredibly special type of functionality and special type of stability. And this is an organic 2 problem. Okay, so this semester, don't touch these puppies. Okay, don't touch these puppies. But what I'm trying to show you is these are special. These are not considered alkenes. Okay, and up until next semester, this guy right here is what we call benzene. Okay, and until next semester, don't you touch benzene. And then we actually have two chapters just over benzene molecules alone next semester. Okay, but again, okay, what aromaticity means, what aromatic means, we're not going to teach you until next semester. But again, just recognize I don't touch this until I graduate from Organic 1. Okay, and so we have different ways of classifying carbons within a molecule, which will actually dictate a pathway of chemical reactivity and the kinetics of the chemical reaction, believe it or not. Okay. And so it's relatively simple. Okay. If the carbon is attached to just one carbon, it's referred to as primary. If the carbon is attached to 2 carbons, it's called a secondary. If the carbon is attached to 3 carbons, I know, that's what's tricky. It's called tertiary. And if it's attached to 4, it's called quaternary. Okay. And again, we're just talking about hydrocarbons here, but we're going to use the same type of classification for different types of functional groups as well. Okay. For example, okay, I have this hydrocarbon here. This is just a flat out hydrocarbon. And if I go and I label all the primary carbons, okay, these are typically terminal, which means they're at the end of a stick, if you will. Then we have secondary. Okay, so I have 1, 2. Oops. I'm going to draw this line in here because I just realized I didn't give you guys any tertiary, which means that gives me 1 more primary. Okay. Then we've got the secondaries here. Okay. Now we've got the tertiary that I just added in, which is right there. And last but not least, we have a couple of quaternary, which are here and here. And so, again, being able to identify what type of carbon it is, okay, will predict the pathway of chemical reactivity starting in chapter 12. So you need to be good at that. And then at the end of chapter 5, we're going to be using this for example, for doing spectroscopic analysis. So this is going to come up over and over and over again, okay? And so again, don't get tricked out when we start adding in heteroatoms, all right? This right here is a, oops, let me use the same colors. This right here is a primary carbon because it's only attached to one carbon. Whereas this right here is a secondary carbon because it's only attached to two carbons. And this right here is a secondary carbon because it, again, is only attached to two carbons. So we're not going to count this nitrogen group, okay? And then this last one here, okay, this last carbon right here, oopsie, is a primary carbon because, again, it's only attached to one carbon, okay? And so when we're talking about the type of carbon it is, primary, secondary, tertiary, quaternary, we're only talking about how many carbons it's attached to. All right, and so that's important that you understand that distinction. All right, so this is pretty much everything we're going to see this semester in terms of chemical reactivity, except for this guy right here. Okay, the one that I put the star next to, that's a next semester problem. But everything else, we're going to talk about the chemistry of them this semester. Okay, the first one is an alkyl halide. An alkyl halide has this general structure, or again, you've got some carbon chunky here attached to one of these four halogens. Okay, and so this is how you identify them. So an alkyl halide could be this guy here with a fluorine. It could be this guy here. Oh, hold on, I'm kind of like in a cyclic mode right now, aren't I? Where I have an iodine here. Now, obviously, these are different halogens, but these are both classified as alkyl halides. The X group, whatever it is referred to as a halo group. Okay? And so you should have learned this when you were learning about the periodic table, right? 7A is referred to as the halogen group. Okay, so that's fluorine, chlorine, bromine, and iodine. Okay, and so that's the halogen family. Those are referred to as halogens. Okay. Alcohols, okay, they have this OH right here. Okay, methanol is a very common alcohol. It's called wood alcohol. The OH on an alcohol is called the hydroxy group. Okay, and again, okay, there's a bunch of different alcohols out there. This is what we call hold on, come on. This right here is called ethanol. This is the alcohol that we drink. Okay, we have aromatic alcohol. So here's my benzene ring. But because you have that telltale OH, these are both alcohols. Okay. Ethers, very common. So instead of having an OH here, they have an ROR, right? This guy right here, okay, you've got your two R groups flanking this oxygen atom in the middle, okay? And the OR group itself is called an alkoxy group, okay? And so now the oxygen can be part of the molecule, the core molecule. With alcohols and alkyl halides, okay, the OH or the halogen is just kind of off on its own, right? They're always going to be terminal. They're never going to be the central atom. But with ethers, you can see them, the oxygens, as a central atom, okay? And so, again, we're going to talk about these in gory detail, but this is an acyclic ether, and that's a cyclic ether, okay? But both of them have what? Okay, the O in the middle. Oops. Have the O in the middle, and then the R group on either side. Only for the cyclic ether, the R group loops around, okay? Next one is called an amine, okay? The NH2 group is called an amino group. Now, we're not going to talk about their chemistry until next semester, but we do use these guys a lot as solvents, okay? And so if I'm going to zoom in here, they also come in a couple of different flavors. If the nitrogen is just attached to one carbon, it's called primary. If the nitrogen is attached to two carbons, So this 2R or R2 would be something like this. Okay. And so the R's would be these guys on either side. This would be secondary and this would be tertiary. Okay. And so the basis of comparison for these guys is ammonia. And we all know that this is a base, which means all of these amines are also basic. So we'll be using them this semester when we need a base, sometimes as a solvent, sometimes to clean something up. Okay. And so we use these a lot to help us finish our chemical reactions or support our chemical reactions. Okay. The next one, again, is an SH group. And so I know you guys have got to remember a lot of stuff. But if you look at alcohol up here, it's OL. If you look at thiol over here, it's SH. And alcohol, it's OH. Okay. And its functional group is called a mercapto. Kind of cool, mercapto. Okay. These guys are stinky little guys. This is what gives people BO, foot funk, chronic halitosis, because mercaptos are very typical for biological decay, bacterial metabolites. Okay, that's why things that are basically decaying smell that bad because of these puppies. And so the biggest difference between thiols and sulfides is the same thing as the difference between alcohols and ethers. Okay, alcohol, you have that terminal OH ether, you've got an O with R groups. Same thing here. Thiols, you've got that terminal SH, where the sulfide, you've got two R groups on either side of a sulfur atom. So again, there's some similarity here. Okay, but again, just like before, we could have a sulfur in the middle in a cyclic species. So we could literally just take these two compounds that I use for alcohols. I'm sorry, that I use for ethers, and cut and paste them here and just replace the oxygens with S's. Okay. And these are called alkyl thiol groups. Okay. The SR groups are called alkyl thiol groups. Okay. And so again, this is almost everything that we're going to cover this semester in terms of the chemical properties of these puppies, plus the hydrocarbons. So for organic 1, we're going to talk about the chemical properties. Yes, sorry. Hydrocarbons, and then basically everything on this page except for amines. Okay. All right. And so let's talk about how we classify these as well. So we can also classify these as primary, secondary, tertiary. It's a little different for some of them, but I'm going to start with the simplest. Okay. And so for being able to classify them as primary, secondary, or tertiary, here, we're only talking about alkyl halides, alcohols, and thiols. Oops. And then we're going to have a special classification for how we look at amines. Okay. So for alcohols, thiols, and alkyl halides, we do it the same way. Okay. If I'm just attached to a CH3 group, okay, and so in this case, this could be X, this could be OH, or this could be SH. Okay. This is what we call a methyl. Okay. And then whatever. So methyl alcohol, methyl thiol, methyl halide. Okay. And so that's how we classify them. Okay. Because that carbon's not attached to any other carbons. Okay. So it doesn't fall into the primary, secondary, tertiary category. Now, if I have something like this, or again, I have an X, an OH, or an SH, these will all refer to as primary. So primary alkyl halide, primary alcohol, primary thiol. Okay, so all of those terminal groups are attached to, okay, carbon that's only attached to one carbon. The flip side for this, and I think you guys are starting to get it, hopefully, if I have something like this, where I have an X here, an OH here, or an SH, this is called a secondary. because again, they're attached to a secondary carbon. If I have something like this, where I have either an X, an OH, or an SH, these are referred to as tertiary, okay? And so, again, the types of chemical reactions that these puppies undergo depend on what we call their substitution patterns, okay? Primary alkyl halides do not undergo the same types of reactions as tertiary alkyl halides under some conditions, okay? And so it's already starting to be complicated, right? So at the bare minimum, by the time we get to those chapters, you need to at least be able to identify what type of an alkyl halide, what type of an alcohol, what type of a thiol you have, okay? We don't do this for ethers or sulfides because why? Well, oxygen and sulfur form two bonds. So it doesn't matter if you have a sulfur in the middle or an oxygen in the middle. You know, we all know that what? They're only going to form one bond, okay? Whereas amines, it's a little different, okay? Instead of looking at how many carbons the carbon attached to the heteroatom is, so that's what we do over here. So over here with these guys, okay, we look at the carbon the heteroatom is attached to. Okay, for amines, it's a little different. We look and see how many R groups are attached to the amino group. I don't know if you guys can hear the thunder. We're getting ready to get hammered here. So, if I'm only attached to one carbon, okay, I'm a primary amine. If I'm attached to two carbons, oops, I'm a secondary amine. And you got it. If I'm attached to three carbons, I'm just going to write it right here. Then what do you think I am? That's right. Tertiary amine. Now, I just happen to write them all symmetrical, but that's not always the case. Okay. So once we make it to chapters A, B, and C, you're going to get a lot more exposure to these. All right. So don't spend a whole lot of brain juice trying to memorize all of this right now. Okay. But that's pretty easy. It's probably one of the easiest things I'm going to teach you. All right. The next classification of compounds are called carbonyl compounds. And they have this generic type of a structure where this could be an H, an R, an N, an OH, an OR, an NH. I'm sorry, NH. I should put that over here. That last thunderstorm, that last thunder was close. Man, if I make it halfway through this video and I lose power, I'm going to be pissed. Okay, and so on and so forth. But what makes them a carbonyl compound is this right here. The CO double bond is very, very special. Okay, CO double bond is a carbonyl bond, and there's a dipole going straight through the middle, partial positive, partial negative. Okay, and there's a bunch of different flavors with these guys. Okay, but here's the deal: if I ask you on the exam what the functional group is, you can't simply say the carbon is a carbonyl. You have to be able to tell me what type of a compound it is. Okay, so we're going to go through these one by one. I'm not going to lie, when I was memorizing these things myself, the H in aldehyde is because it has an H. Okay, right now you're just flat out memorizing. Okay, next semester, trust me, you're going to know these like the back of your hand. Ketones are a little different. Okay, and so ketones have two R groups flanking that central carbonyl. These are somehow how they're abbreviated, so you need to understand how these are. These condensed structures are, because you might see these. Janice Smith uses these a lot. You're going to see these on the ACS final if you hang around to organic 2. You take the MCAT, the DAT, the PCAT, they use these a lot too. Okay, so you need to know that this condensed structure here, okay, means that you have an aldehyde. This condensed structure here means you have a ketone, this means you have something called a carboxylic acid, okay? Carboxylic acids are not anything new for you guys. Acetic acid is the most basic of all carboxylic acids. And just pay attention, this OH here, let me use a different color. This OH here, and a lot of students get this confused, and I get it because you guys are assimilating a lot of information. This is not an alcohol. The biggest difference here, the OH in a carboxylic acid is attached to a carbonyl group, right? Whereas in an in an alcohol, okay, it's attached to an R chunky. That's not a carbonyl. Okay, so that's different. It can be attached to an sp3 or an sp2 hybridized carbon. Hell, it can be attached to an sp3 hybridized carbon. Although I don't remember seeing any alcohols like that. Okay, but the difference is the OH in an alcohol is directly attached to a carbon. It's a CH whatever group. Okay, or here the OH has to be attached to the carbonyl group, and that's the biggest difference. Okay. And as you can see here, the functional group names don't really play through like they did for the sigma bond guys. Okay. We talk about ketone, that's where we typically use the word carbonyl group. Carboxy group, okay, that's here. But you can see that aldehydes, these so-called esters, and amides, and acid chlorides. Well, acid chlorides, I mean, obviously the group is going to be a chloride, okay? But you might also hear these referred to as acid halides. And so I don't know why, but JDOG only uses acid chlorides, but we also see where X is equal to chlorine, bromine, and iodine. So they come in a lot of different flavors, okay? Esters, I think you guys are going to make one of these this semester in the lab, and that's where it's attached to an alkoxy group. So this is basically an OR group, right? And so that's like an alkoxy group. This is, again, an amino group. Oops. And then, of course, the halide group on the alkyl halide. I'm sorry, acid chloride. Alrighty. So, I mean, I don't know what to tell you guys other than start making flashcards. You will learn these like you learned the atomic symbols on the periodic table just by attrition. Okay? But I'm going to tell you right now, you're going to get a question on your exam, and you're going to have to identify which functional groups are present. For example, if I gave you something like this, okay, and I'll bracket it for you because I know sometimes it's hard to tell what I'm asking. So there will be brackets like so, only it'll be neater. And then it'll be labeled A, B, C, and D. And you're going to have to be able to tell me that A is an amino group. B is an alkene. C is an ester. I'm sorry, ether, my bad. And then D, of course, is an aldehyde. And like I said, she talks a little bit about the chemical reactivities in the back of chapter 3. Don't worry about any chemical reactivities until we get to chapter 7, which is going to be after your first 2 exams. So anything that talks anything about chemical reactivity until we get to chapter 7, until you've taken your first 2 exams, don't worry about it. Okay, do not worry about it at all. All right, guys. I will talk to y'all later. Bye-bye.